All right, welcome to the second day here. We've got 4 more exciting tutorials. And to start off, we've got Marco Attene and Marco Livesu. They're both researchers from CNR IMATI, and they're going to talk about geometric techniques for digital fabrication.
Thank you, Ed. So, yeah, I'm Marco Attene from IMATI, and what we will be talking about today is how to exploit geometric techniques to support the quickly emerging digital fabrication technologies. So, what are we going to talk about exactly? Digital fabrication amounts to exploit a computer to control a digital fabrication tool, actually. And, well, historically, the first machine that enabled this kind of control was invented in this very place 72 years ago. And as you can see in this picture, it was quite larger than current modern 3D printers. Fortunately, technology has evolved, and, well, many other cutting tools were invented along the years, such as lasers, water jets, wires, and so on, up to modern days, where additive manufacturing has emerged as technology due to its, well, flexibility and due to the fact that 3D printers are quite cheap. Flexibility is the core here because actually the fact that you can use a 3D printer to produce virtually any shape you can invent has made the market really explode, together with the fact that these printers cost very few money. And as you can see here, the growth of the 3D printing market is exponential. For these reasons, the European Union has set an objective for 2020, which was, well, let's make printing a 3D object as easy as it was before, to print a 2D document on a standard printer. I may say that we have quite reached that objective. Today, if you have a good model, you can just press play and the model is printed. But the bottleneck is not really there. The real bottleneck is how to create that model. Because today, creating a 3D model is still much more difficult than drawing on paper or than creating a picture. So let's see how a model can be created. We have mainly 2 ways. One way is to start from real world. So you have an existing object, and you use a tool, such as a laser scanner, for example, to transform this model into a set of points or a set of triangles. The other big family of methods to create models is to start from ideas or concepts. In this case, you have an idea, and you want to turn it to a 3D model using a modeling software, a CAD software, typically. And in any case, before printing, you must end up to a mesh of triangles. And, but this is just the iceberg tip. Actually, there are many other steps to be undertaken to have a successful print of these models. You may start, for example, from a computer-aided design modeling software to create your initial surfaces. Then the surfaces, which are typically NURBS, or in any case, some smooth representation, must be turned into triangle during the planning phase, which is known as computer-aided manufacturing here. Typically, a company needs another kind of expertise, which is different from the expertise brought by the designers. And this serves to somehow create a process, a successful process that transforms your model to instructions for the printer or for the other manufacturing device you are going to use. And this is the last step. So once you have this object prepared and well-oriented into the building chamber, you need to actually convert some slices into movements of the building tool to actually fabricate the object. So these are the 3 main steps. One of the reasons why 3D print, among all the fabrication technologies, 3D printing emerged is because in this case, the planning of this printing process can be much easier, and in many cases can be made automatically. And well, this is the planning in general. You may start with your smooth surface. We have this nice torus here. You convert it to a set of triangles, and then you use the software to slice these triangles into parallel planes. Then you convert these planes into a set of instructions for your printer, and then you have your model. Okay? Well, yes, 3D printing fails, and it is very easy to make it fail if you do not consider all the subtleties of the process. So even if it's a very flexible approach, it may produce unexpected results, which may cost you a lot, because in this case, this is an example of failure of printing on a titanium powder. The material itself is very expensive, but worse than that, as you can see in this picture, the printed object has deformed, has broken and has deformed. And since 3D printing is a passive process, it might happen that the printing tool hits the object that has deformed, and these printers cost some hundreds of $1,000s, so you don't want to break them. So it's much better that you prevent this from happening. So how can geometry processing help us in this? So we can provide, well, flexible approaches to fit the printing chamber if the model does not fit, or to reorient the model within the chamber, or to create something that help dissipating the additional heat, or to create supporting structures when you have overhangs, or to, well, split the model to make it assemblable afterwards. So this is what we will see in this talk. So this is just the first part of the talk. This is what we will be talking about in the upcoming minutes. And now Cino is going to talk about the fabrication technologies.
Hello, everybody. I'm the other Marco. So now I'm going to talk a little bit about the different technologies that we have at our disposal to fabricate. At the highest level, we can distinguish between two broad categories for manufacturing. We have what is called the additive shape synthesis, which means essentially that we start from nothing and we create an object by solidifying material or depositing material, as in this little video. And this is what we typically call 3D printing. And we also have another technologies which is previous to 3D printing, which is like the most classical fabrication way that we have at our disposal, which is subtractive. This really started when we started to, sculpt something. You have like a big brick, you have a hammer, and you just remove material from your object. And what you want to do is to remove the material that doesn't belong to your shape until your final shape is revealed. So these are the two main approaches that you can have to fabrication. In terms of actual technologies, let's focus on additive synthesis first. We have many different ways of 3D printing. Probably the most famous paradigm for 3D printing is FDM, which stands for Fused Deposition Material. And this is a very simple technology. The printers are actually pretty small. They can scale up to bigger ones, but at least to play with, you can have like a very small printer. And they operate essentially by having this kind of filament of plastic material that goes to an extruder, which is, which is this part here, which is heated. And so by heating the extruder, we melt the plastic filament, and this extruder can move in the space. You have 2 degrees of freedom, plus you can go up and down. And so you can selectively decide where to deposit your material in order to fabricate your final shape. Another approach, which is the one that was mentioned in Marco before, is printing on metal. In this case, you have a laser that, through a mirror, is hitting the surface of a chamber, which is filled with some powder of titanium or of other alloys. And what you do is to selectively melt the powder in order to solidify the shape that you want to create. You have mainly two approaches here. You have what is called SLS and SLM. SL stands for selective laser, so it's common to both acronyms. And then you have sintering and melting. So if you imagine a single grain of your powder as a sphere, when you do melting, it means that the whole sphere is completely melted, and so it can glue with adjacent material. When you do sintering, you can imagine that the core of the sphere doesn't melt, so it remains in its initial state, and you just melt the outside in order to have the binding with the other material. And of course, depending on which approach you use, you get different physical properties. Another very popular approach is stereolithography, or SLA. In this case, you have a tank, which is going to be this part here, which is filled with some resin, which is in its liquid state. And this resin reacts to UV light. So when you expose the resin to UV light, essentially the resin solidifies and becomes thick. So what you do is to have an UV projector, which is projecting a binary image on the surface of your tank. And so you are selectively deciding what to solidify and what not. And once the layer is solidified, this platform goes up, and so you are fabricating your object layer by layer. Eventually, we have this technology which belongs to HP Jet Fusion, Z Corp, which is called droplet. In this case, you can imagine that, again, you have a tank which is filled with some material in its powder state, and then you have a big grid, which is, again, sort of a binary image. And for every single pixel in this binary image, you can decide whether to drop a little material or not. This is why this technology is called droplet. And if you decide to drop some material, this is going to be some material that glues the material that you have in your tank and solidifies it. And with this technology, you can also plug, for example, color information, or you can decide to what extent you want to make the material stiff so that you can have like a variable stiffness. So it's a very versatile technology. And this is pretty much completing the taxonomy, a broad taxonomy for additive synthesis. If we look at these technologies, we may see that we have FDM, which operates by local deposition, and then we have a bunch of other technologies that operate by what I'm calling here layer solidification. These machines have something in common, as I said. They have kind of a container which is filled with some material which is not in its final state, and we decide that we want to solidify or melt this material. Another distinction that we can make is between vector approaches and raster approaches. So for the FDM, in which we move the extruder along continuous paths, or with the laser on powder, in which we drive the paths of the laser with continuous path, we have a vector approach. And the benefits of this is that you get infinite precision and everything. Approaches like stereolithography and droplet are intrinsically discrete because, as I said before, you have this kind of binary image, which is the slice of material that you want to create. And so you have finite resolution, which is sort of a limitation. But on the same side, it's much easier to play with these approaches because you are playing with binary images, which are really easy to deal with. OK, now let's move to the subtractive synthesis, in which you have this kind of drill bit, which is penetrating the material and carving material away to reveal your shape. In this case, all machines pretty much are done in this way. You have a drill bit which rotates, which is going to be the blue arrow here. And then you have a bunch of degrees of freedom, which allow you to move the drill bit in different places. And depending on how many degrees of freedom you have different machines. The simplest ones are the 3-axis milling machines, in which you have, as the name suggests, 3 degrees of freedom. So you can move the drill bit in 2D, like for the FDM technology, and then you can go up and down, which means that you can carve material away only from top to the bottom, which really restricts the type of geometries that you can create, of course. And then you have a slightly improvement with 4-axis milling machine, in which you can also have this C degrees of freedom that allows you to rotate the part along an axis. And the most versatile one is the 5-axis milling machine, in which you can also rotate the drill bit, which allows you to carve material away from an angle rather than from top to bottom. And of course, the fewer degrees of freedom you have, the easier these machines are to program. The more degrees of freedom you have, it becomes more complicated to program the machines in terms of deciding what are the tool paths that the drill bit has to take in order to remove the material and reveal your shape. On the other side, 3-axis machines allow you to only create very simple shapes, height fields. We will say something more about this during the presentation. And for 5-axis, you can create much more complex shapes. Okay, so now Marco is going to tell something about how to model for fabrication.
Okay, so as I mentioned in the beginning, modeling is the real bottleneck here. And well, when modeling 3D objects, we must also consider that fabrication is quite a demanding applications because, well, there are some common requirements for any fabrication technology you may consider that, for example, the model must represent a solid object. This might seem obvious, but in many cases, when you model objects, you don't have this requirement satisfied. Even if you use advanced CAD modelers, you may end up with objects like this, which seem to be well defined, but if you zoom in, you can see that there are tiny defects and gaps. And well, even if these things are hardly visible for a human being, these might easily spoil the printing process because you cannot slice effectively the object and transform the object into continuous movements of the printer. Then there are requirements that depend on the specific technology you are going to use. For example, if you print using a powder bed technology, what happens is that in the end of the process, you have to, well, absorb the remaining powder and extract the object from it. And you can imagine that if you have an object like that with a closed void, what happens is that if you produce it using such a technology, you would have the excess powder trapped into the cavity. And this is, of course, not what you want. So modeling in these cases must predict these configurations, and you may want to create proper evacuation channels to remove that excess powder. Another example of thing that you must consider before modeling for fabrication is the thickness. Any machine that creates real 3D objects has some limitations. For example, filament-based 3D printers can extrude filaments with a given thickness. So if your model has thinner parts, what you end up is probably something unexpected, such in this picture. In these cases, you may want to thicken these parts properly, but this is a quite tricky process. Another problem you must consider is if you have, well, moving parts. In this case, you have many gears that are supposed to move with each other. This can be done with 3D printing, is perfectly feasible, but you must consider that there must be some clearance between the objects, otherwise you may end up with something like this. And, well, the plastic may be glued together in an unexpected way, and the functionality of what you print is no longer what you want. And, well, a big issue with fabrication technology, with layered fabrication in particular, and is the presence of overhangs in your models. Overhangs are, well, parts of the model that, for example, if you use subtractive manufacturing, prevent you to reach some of the parts that you need to carve. As you can see, all the yellow part is not reachable by the drill here, so you cannot produce. This is exactly what Marco was saying when he was saying that 3 degrees of freedom milling machine can only produce height-filled objects, such as this one on your left. But overhangs are an issue even if you use additive manufacturing, because in this case you need to depose material somewhere, and in these cases you have no places where to depose your material. And for these cases you need to create some support structures, and we will talk about that later in this talk. There are also limitations regarding the size. Of course, each 3D printer has a built-in chamber, and you cannot build things which are larger than that. There are some approaches to split objects into smaller parts that you can print one after the other and then reassemble them afterwards. Probably Marco will talk about that later. Other issues to be considered is the use of material and the printing time. In this case, you may tweak with the orientation of the object within the building chamber to avoid the need to build too many supporting structures that consume material, or to minimize the height of the object in the building chamber so that it takes, well, shorter times to produce. Another big limitation is the fact that many low-cost 3D printers actually can print using one material at a time. And if you want to use these low-cost 3D printers to produce multi-material objects, such as this one, you might need geometry to be partitioned into pieces. Each of them must be buildable with a single material. About the quality of the surface, when 3D printing or fabricating in a layered fashion, you can observe something which is very similar to the classical aliasing when rendering. So this happens because you are using a fixed grid of pixels for your images, and very similarly it happens when you print, because you are using a fixed resolution. The only difference that when you print, you have a lower resolution in the Z, well, the vertical direction, and this is something that you can exploit to find orientations of your object into the built-in chamber that optimize the quality, because of course, since aliasing is not the same in all the directions, you may choose the one that optimizes the quality of your print. And if you have complex objects, you can even choose to split these objects into separate parts so that each can be oriented optimally for the sake of surface quality. And the geometry processing can also help us to create voids when modeling into the objects so that they have a certain wanted equilibrium, and this is something which is very useful to create, well, nice objects like these in this video here. So this is mainly what we'll be talking about. What we will not talk about during this lecture is model repairing. Model repairing is very related to 3D printing because, as I was saying, invalid 3D models may spoil the process, but this would require a whole lecture on its own, and I point you to my previous courses at SGP in 2013 and 2019 for this. We will not talk about residual stresses and distortions of the objects being printed. This is something very interesting, but this is well, slightly out of scope for this kind of audience. And we will not talk about combined additive and subtractive manufacturing. This is something very useful because you create a slightly larger stock material object using 3D printing that then you can finally refine using subtractive technologies, which are typically more precise. Okay, so this moves to model orientation, and Chino will talk about that.
Okay, so with this part, we begin to talk we begin to talk about what we call the process planning pipeline. You can imagine the process planning pipeline as a black box in which you input your 3D shape and you output the machine instructions to create your 3D shape with the machine that you have at your disposal. And the first part of this is how to select an orientation for your model. So we take in input an object in the reference system in which it was modeled, for example, what we call the object space typically. And in the orientation part of the process planning pipeline, what we do is to find an orientation for the object which is going to be the orientation in which we will fabricate it. Typically, we will have the z-axis, which is going to be the normal of all the planes, for example, for layered manufacturing. This choice of the orientation of the model, as Marco anticipated, has a huge impact in the success or the failure of the print. And here you can see a very simple shape like this L in 4 different orientations. And every single orientation gives you different properties. For example, in the first 2, you may notice that the surface of the object is perfectly aligned or perfectly orthogonal with the build direction, which means that in terms of surface finish, everything will be fine. The first one is slightly worse than the second one because you have more slices. And this typically translates into a more time-consuming printing process. This is because, although the volume of the object is the same, typically having more layers takes more time because every time the machine has to change layer, it's a time wasted. Sometimes, for example, with the FDM technology, the printer may want to clean the nozzle before switching to the next layer. So there is a lot of stuff that is just wasted time in terms of efficiency of the printing process. And the rightmost orientations, you can see that here we have overhangs, which need to be sustained. So if this will be the orientation of choice for our print, then we will need additional material to sustain our object from below. And so in terms of cost of the print, in terms of cost of the material, we will pay a higher cost. So this is just to make the point, the orientation is very important. Let's take a closer look at the staircase effect, which is one of the dominant aspects of the orientation in 3D printing. So let's say that this is the object that we want to print, and this is going to be our build direction. And if we slice this object and we decompose into different slices, what we may notice immediately is that in the places where we are nearly vertical, the approximation of the surface is pretty much decent. It's not perfect, but it's decent. Of course, here, I'm using very coarse slices, very, very thick slices, but if I decrease the thickness of the slices, the approximation will be even higher. But here, no matter how thin my slices will be, I have an higher error. So in general, what I can say is that the error that I have when I am nearly horizontal is much higher than the error that I have when I am nearly vertical, which means that when I choose my orientation, I really want to penalize large portions of my surface to be in a nearly horizontal fashion, because otherwise the quality of my print will be low. And here you have a concrete example. Again, here we are using very thick slices just to exaggerate the impact, but you can see, for example, that if this is the build, if this is the build direction, here I am nearly horizontal, and the resolution of the legs is really horrible, and the same goes here. For example, if I use shape decomposition to address this issue, and I decompose the shape in order to have nearly vertical configuration pretty much everywhere, for same thickness of the slices, I obtain a much higher quality approximation of my object. So this is something that you want to consider when you choose the orientation of your object. Of course, there are multiple metrics that you can consider when you choose the orientation for 3D printing. And here you have like an overview of the most common ones. You want to minimize, for example, the support structures, because this is additional material that you don't want to waste in this way. You may want to minimize the height of the object to compress the printing time. Or also the fidelity, the geometric fidelity, which means the staircase error, as I just shown, but also to be smart, for example, in choosing where do I position the linking points between the support structures and the object in order for these linking points not to be in visible places. This is because when you complete the print and remove the support structures, typically you leave some artifact on the surface. And so, if, for example, if you print a statue, and the print and the linking point is like in the nose, it would be like really, really visible. Whereas if you put it like on the back of the head, it's much better because nobody is going to pay attention to that. So even if you have an artifact, it's not a big deal. And this is something, again, that can be optimized at this stage of the pipeline. Also, functional-wise, optimization of the orientation. For example, if you know that your object is going to be solicited in a specific direction with some forces, you can choose the orientation of your object in order to be maximally resilient to that solicitation when you choose the orientation of the print. The problem with optimizing the orientation direction is that the landscape of the functionals that you want to optimize are not really nice. in the sense that typically these are non-convex functionals, and they contain lots of local minima. So if you want to optimize this, it's not easy. For example, in this case, you can see this orange part, and here we have 4 plots, which are essentially plotting the function that denote the supporting area, the building time, the surface roughness, and the surface quality. What makes things even worse is that typically you want to combine these things. So you want to find a good trade-off. And the problem is that you have conflicting objectives. For example, for build time and surface roughness, when one function goes down, the other goes up. And so you don't really know what to do here. And this is typically solved by the user. So the typical approach is to kind of automatically select a bunch of potentially good orientations, and the final choice, the final trade-off between these quantities will be made with the user in the loop because it's a critical decision. So this is an example of a typical pipeline to optimize the orientation. What you do in the first stage is to sample the space of possible orientation for your object. For example, here we're sampling with a spherical Fibonacci the sphere. So every single point will be a candidate orientation for our object. And this can be like a uniform sampling of the orientations, but it can also be driven by some information. For example, the saliency of the surface that you want to create. For every single sample, you know how to estimate your error, because it depends, for example, on the orientation of the surface, the angle that it forms with the build direction that you are considering. So these are quantities that you can consider and compute to get actual numbers about the quality of a specific point. Once you have this, you select, as I said before, a bunch of points, critical points in this functional, which seem to be promising to give you like good orientations, and eventually the final choice, for example, in this specific case, was made by the user, as I said. Given the nature of these functional escapes, genetic algorithms and simulated annealing are often used to optimize these functionals, because you get like very crazy spaces in which local minima are really like scattered, and so it's really difficult like to follow the gradient and land in a very good local minimum. It's hard to be sure that this will happen. Okay, so now we're going to move to the second part of the process planning pipeline, which is the slicing. So in the slicing, we take in input the model in its final orientation, which we just decided. And what we want to compute are the contours that are going to become slabs of material. For example, in FDM printers, they will become like slabs of material that we deposit through the extruder. In this part, we have mainly 2 topics to address. First of all, where do I position the slicing planes that are going to define my contours? And secondly, how do I efficiently compute these contours? Because I need to intersect the slicing planes with my mesh, right? The objective that we have, of course, is the accuracy. We want to be as accurate as possible, because this is going to create, of course, an approximation of the geometry that you have in our mesh, and we want this approximation to be the best as possible. So the most trivial choice that we can do is to choose a uniform slicing. So the distance between adjacent planes that cut the object in flat areas is always the same. The problem with this approach, as I said, is that when you are nearly vertical, everything is fine. So we have a very nice approximation. Where we are nearly horizontal, we get a much cruder approximation. So if we have a budget of slices that we have at our disposal, we may want to optimize where to position the planes in order to have more planes when the surface is more critical, is misaligned with the building direction, and less planes when it's less critical because it's a nearly vertical configuration, so we know that it's going to be good anyways. And this can be done because many machines can play with the thickness of the material. For example, in FDM, you can decide to deposit a little bit more material, and so you have some degree of freedom to make sure that the slice will be thicker or thinner, depending on what you want to achieve. So to do this process, we have mainly 4 different approaches. We can be driven, for example, from the local error. So this is the geometry that we want to fabricate. we can, depending on the orientation of the surface and the angle that it has with the build direction, we can partition the surface into regions which can be more or less critical depending on how they align with the build direction. For example, here you can see green when I am nearly vertical, orange where I am kind of in between nearly vertical and nearly horizontal, and then red when I have the maximum error. And if I have this, I can just decide to position more layers where I have the red regions because I know that that is the place where I will have more error. So that's one option. Another option is to start coarse and to then refine in the regions which are more critical. So we start with very thick layers, so thicker than the layers that we will have in the final result. And for every single layer, we take a look at the geometry that is trapped in between two planes, and depending on the orientation of the surface in that portion of geometry, we decide whether we want to add another layer or not. And so we just continue like this, refining when it's necessary, and eventually we get an adaptive slicing which positions more slices where it's more necessary. We can also do the other way around, so we start with more layers than we want to obtain in the final result, and we just continue by merging adjacent layers in regions which are nearly vertical, like this. The process can be also completely optimized. So in 2017, it was proposed a global optimization method which optimizes this thing. So essentially, given a budget of slices, it optimizes for the error that we obtain. And not surprisingly, this approach based on numerical optimization, it is more costly than the previous ones, which are greedy and therefore easier to implement and also faster, but it gives you the best results overall. Okay, so now let's say that we have our slicing planes and we want to compute the contours. What we need to do is to start with our geometry. So this in black will be the triangles of our mesh. The orange one will be a slicing plane. And so we want to compute these intersections in order to create loops that are going to define the polygons, which are the geometry of the slices. This process is pretty simple. There is only one issue with the robustness of the process. Because due to the limited numerical accuracy in the computers, anytime you compute intersections, it's not always a nice thing, in the sense that you may have errors which depend on the approximation of the floating point system. For example, in this case, I just picked a slice which passes through a vertex. So when you compute the intersection between this plane on the top and these triangles here, depending on the numerical approximation of the system, you may or may not catch consistently that intersection, which means that you are going to, taking all the intersections and try to close your loop, you may have gaps, you may have like duplicated information, and so it's not a robust approach. A good way to overcome these issues is to consider your building direction to create sort of an height field which is encoded in the mesh. And in this case, you can essentially use contouring algorithms like marching cubes and its children to create contours which are robustly extracted. And this can be done, if you want to create 1D contours, can be done on a triangle mesh. If you have a tetralization of your object, you can also get the interior of the slices, because you are essentially marching on the volume of the object, and so you get also the interior of every single slice. And this is pretty robust. Final topic regarding the slicing. This is a more recent approach and regards the ability to create non-planar slices. So far we've always said that the slices are planar. And one of the issues that depends on the planarity of the slice is that if I have a geometry like this orange one, I create a lot of this staircase effect because the build direction doesn't align with that particular part. Playing with the freedom and the flexibility of some printers, I can create sort of carved layers that align better with the geometry. And here, the main idea that we see in the literature is to essentially define a function that goes from my object space, which is the orange contour, to some other space, which is depicted here in this box. And essentially what I do is to create planar slices in this space, and then the pullback of these slices is going to create the curved slices, which we use for fabrication. And this is done in many different fashions in literature. The major difficulty in doing this is, first of all, to make sure that the fabricability constraints are preserved when you move to your slicing space. Oh, here you can see an example, like a concrete example of a staircase effect using non-aligned, using classical slices, and the same geometry with curved slices, which nicely aligns with the geometry. So what I was saying is that one of the major difficulties for these approaches is, first of all, to make sure that the fabricability constraints are met when you move to another space, because essentially the function that creates such a mapping has to be constrained somehow in order to make sure that it creates something that is fabricable. And secondly, since we don't have anymore this property, for example, in FDM of the extruder, to be able to move everywhere in the space because everything that I've already printed is below the extruder. When I have curved slices, it may happen that the extruder hits some parts of the object because they are not planar anymore. And so avoiding those collisions is an issue. So far this is done very heuristically. Essentially, it's a trial and error. If you try to apply your pipeline, do the mapping and the slicing, and if you realize there is a collision, you cannot try again because it's very difficult to incorporate global collision detection into this mapping system. Okay, so now Marco is going to talk about supports.
I'm not sure you want to have a technical break, but otherwise I can just wait.
We could have a quick break for questions, you think?
Yeah, maybe, yeah, if there are questions.
I had one clarification to ask. When you're doing like the sampling on the Gauss sphere, like the space is three-dimensional for rotation, so I guess is there, or am I misunderstanding something? I guess this was the, I think it was the slide on like model orientation, and it looks like you sort of just sample, you like sample a bunch of candidate orientations.
Yeah.
And
This one.
It's a solid. Is it a solid ball? And you're
Yeah.
sampling the interior as well. Okay.
No, only the surface.
Only the surface.
Yeah.
Okay. But the space of rotations is 3D. You know.
Yes.
Yeah. So I was just wondering how do you, because this is just the 2D. This is like the sampling on the surface, and then there's like.
On the surface of a sphere, yeah.
Okay. And wouldn't there be like a?
So you can see it this way.
Dimension to consider?
Every single
Yeah.
point of this sampling of the sphere
Yeah.
will give you a vector which connects that point with the center of the sphere,
Right.
and that will give your Z direction for printing.
Yeah.
That's the idea.
Oh, okay. Okay. So like the additional like rotation.
Yeah, you have another degree of freedom, but that doesn't really matter.
Degree of freedom, it doesn't matter.
Yeah.
Yeah.
Okay. Okay.
I see what you're
You don't care about that one because whatever it is,
Okay. I see.
for print-wise, it doesn't really change.
With the slightly curved slicing,
Yeah.
is that common, or does that exist in like consumer printers? You're showing that that video of with the full-on robotic arm, with however many degrees of freedom, but does that exist on even at a lesser extent on like consumer grade printers? I've never heard of this.
No, this comes from a research lab. As far as I know, there is no like a commercial facility like this.
So it's just super exotic.
Yeah, super exotic.
All right.
Is the curvy slicer possible on a SLA printer where you are exposing? So like on a
For
thicker.
stereolithography, you mean?
Hmm?
For stereolithography,
Sorry?
SLA, you said.
Yeah, SLA.
So print on resin.
Yeah.
I don't think so. Yeah, in that case, no.
Yeah.
So these are. So this paper shows results only with FDM. Oh, sorry, this one. Okay. So these are like a classical extruder filament, and they have some degree of freedom because some of these printers, for example, you can tilt the plane, you can play with some parameters, so they will give you some flexibility. With stereolithography, you are more constrained because the surface of the resin in the tank, even if you tilt the tank, it doesn't really work.
Yeah.
Stereolithography, is it my imagination, or were there systems that used multiple laser beams to pinpoint?
Use a UV projector, and project a binary. Well, there are many different fashions. The one that I talked about is the one that has a UV projector that projects a binary image, which is going to be like a thick voxel, this is part of the object, non-thick voxel, this is outside of the object.
But are there systems that use, say, two lasers to intersect at a given point in 3D and just fuse that one point without needing supports and things like that?
I'm sorry, I didn't understand.
If you have two laser beams that intersect at a point in 3D,
Two laser beams?
I'm not aware of any technology that exploits this approach, but might be an idea.
okay.
I don't know, maybe you are aware.
No, I'm not. I was just curious. I thought I had seen such things.
Yeah, but it might be an idea.
All right, thank you.
Actually, I was just curious for the layer thickness variation. You mentioned like FDM can do that. Is that also possible with like the other printing types, or is there like some
So
variation in that capability?
all the papers that I'm aware of demonstrate results with FDM.
Yeah, like I was wondering if you had like the sintering approach or like the UV
I've
light
never
thing. Like
seen-
it's not possible to vary the layer
I
thickness in
don't know
those
if it's
instances.
physically impossible, but I've never
No,
seen
no
it.
one does that. Okay.
Well, just as a follow-up of the question before for non-planar slicing, I'm not associated with them, but there's an open source project by the University of Hamburg named 3D printing of non-planar layers for smooth surface generation, just in case someone's interested. I think the results are really good, and I just wanted to share.
Okay.
Yeah, if there's nothing, perhaps we.
This one?
Okay, so we can proceed. Well, okay, and another thing that we need to consider is so-called support structures. I mentioned them, and Chino also mentioned them. We have two kinds of supports, actually. We have so-called internal structures, which are something that you print inside the object and will remain there after the printing is removed from the fabrication tool. And external structures that are actually just auxiliary structures that you use to aid the fabrication process and will be removed after printing. Supports are necessary in various cases. They may depend on the technology, but typically if you use material deposition, you may need supports if your model is made of several connected components, because of course you don't have any place where to put one if you do not use supports in between. Or if you, of course, if you have overhangs, or if you have so-called islands. Islands are these places in the M letter there, because when you slice and you reach that point, you need some support. If you have cavities and you use SLA, for example, you still need to remove the resin from there. But supports are not only necessary to sustain the object, they might be necessary for other things. For example, to avoid too large distortions. Material, when heated, tend to glow. Well, when it gets cold, tends to shrink. And this, if you have long filaments in your FDM printing, this tends to detach from the lower layers and deform the objects. What you can do for that, to avoid this, is to add supporting structures that keep the material in place. And if you print using metal-based powder, well, metal powders, this would also help in resolving these high temperature gradients because it helps dissipating the heat from the object being printed to the building platform. So there are many cases where we need supports. But now we focus on internal supports. When you print an object, in principle, you can just fill all the internal parts of the objects using the material using to print, this is certainly feasible, but of course, it's a waste of material. On the other extreme, you can print only a thin layer of the surface while keeping the internal part empty, but this would result in very weak objects that would break too easily. So what we want to have in the end of the day is to actually have, well, halfway a trade-off to fill, to partially fill the internal parts of the object with just enough material to make it structurally robust enough. Okay, to create internal supports, we must first make room for them. So what typical approaches for this include hollowing. So we just want to create a thick part of the surface. Then when you have these cavities within the object, you need to create either sparse or dense infills. So these are trajectories of the toolpath that create some thin walls in the object. Or you can have sparse internal frame structures, such as in this picture. This is quite different because this uses less material and create many cavities. Or you can even create microstructures to simulate some particular behaviors we will talk about. But let's take each of these steps on its own. To create, to make room for internal structures and to create these cavities inside the object, you can use morphological erosion, for example. So you may create offsets and grow and shrink the object just enough to create the surfaces that enclose the thick part of the object. And you can do that either on the level of the 3D object or at slice level. So you take just each of the polygons that represent a slice and create an offset of them. Then you can fill in the object. These these trajectories that the building tool follows to create the infills have a strong impact on the thermomechanical characteristics that the final object will have. I will not go into details of that because this will bring us too far. Probably Marco will tell you something more during the toolpath generation, but just a little bit. And well, the tool, a good design of toolpaths might even give some aesthetical properties to the object that you may want to achieve. When it's, if you choose to create sparse internal structures in your objects, you must consider that not all the technologies are suitable for that. If you use, for example, FDM, some internal structures can be created, but these kind of structures cannot be created if you use, for example, powder bed machines, because powder would remain trapped into the cavities. Even if you use FDM, you must consider that these internal cavities might require support, and that would be a problem because supporting structures would remain trapped in the cavities also. So some approaches create self-supporting cavities, meaning that the walls that create these cavities have overhanging angles just small enough to be self-supporting. And some of these approaches are optimized to support the forces in one direction. Some others have no preferred directions. And then this microgeometry. Microgeometry can be used to simulate the behavior of some stiff, rigid material. Can be used to simulate rubber-like materials. So you can use plastic, for example, to create something which is flexible as you want, depending on the microstructure that you use inside. And okay, let's talk about external supports. As said, external supports are sacrificial structures that you will remove after the printing. The typical example is this one. If the building direction goes from bottom to top, at a certain point you need to print that island there, that print dot, and of course you have nothing to put the material on. So that is a typical example where you need support. The other example is this one. So you have objects that have overhangs, and up to a certain point, the tension of the material is sufficient to keep material in place, but if the overhanging angle gets too large, then you need supports again. And this, the threshold angle for this really depends on the kind of material and on the technology you are using. In this example, we see a model within a canonical orientation on the bottom left, and you can see it printed using FDM without supports. So as you can see, it's a complete failure. Or you can see it using supports on the upper right part, and after supports are removed. So the process is typically divided into 3 phases. You first need to detect which parts of the object require support. Then you need to generate the actual supports, and you have various choices for that. And in the end, after the print, you need to remove them. So to detect the need for supports, you can use the surface directly. So triangle by triangle, you observe the normal direction, and you see if this is facing down to the building platform with certain angle. If so, you tag that triangle with needing support. Or you can do that at the slice level. So you take each of the polygon representing the slices, and you see if any upper polygon is contained in a lower one. If not, you have something that needs to be supported. Or you can even do that at toolpath level. So you see exactly what the machine is going to do. So if the machine is going to depose material in void space, that would be a problem. Then you need to generate, when you know where you need supports, you need to generate them. And here you need to trade off between the printing time, the material that you want to use, and the reliability of the supporting structures. You may decide to use dense supports, such as in this picture. This is the typical standard approach that is provided by commercial slicers. This is very robust and reliable. Otherwise, you can use some more sparse approaches, such as this one. This allows you to save a lot of material. The drawback of these approaches is that these structures tend to oscillate during the printing process, and this is, makes the process a little bit more delicate. In more recent approaches, you may create some scaffolds instead of supports that exploit the fact that the material you are using has a sufficient tension to create actual filaments that go from one support to another. Even if they have not a perfect geometry, they may bend a little bit, but they are sufficient to keep other material upon them to create actual supports. And this is the approach of this work that creates this very sparse supporting structures, which are scaffold-like structures like this. So we can have a quick comparison of what we have. We have, for example, MakerWare, which is quite a standard software that creates very dense structures, dense and stable. Or otherwise, you can use Mesh Mixer, which is quite diffused software that creates sparse structures like that, or Photoshop CC. Or you can use this scaffolding like structures. So these are, each of them have advantages and disadvantages, but usually the trade-off is between the use of material and the stability of what you're creating. And the last step is the removal of these supports. The removal can be quite challenging. If you have objects like this, you may have lots of supports in all the places of the object, even inside. In these cases, there are no cavities, but it is quite hard to get into the object to remove these supports after printing. So for these cases, some printers support dissolvable materials that, well, you can just take the object along with its support and put it in water or other solvent, and well, one of the material, the one that is used to create the supports, would dissolve while leaving the object free of them. Of course, to exploit this, you must have a printer which is able to extrude two different materials, one for the object and one for the supports, and these are called dual extruder machines, which, well, they are quite diffused and cheap enough to be used. And yeah, I think I can give the floor to Marco.
Okay, so now we're going to talk about decomposition. This is actually an optional step. It's not necessarily involved in the process planning pipeline, but we had to talk about it because there are many different approaches to it, which is relevant for fabrication. Shape decomposition is used a lot. There are lots of papers that use it to overcome the limits of the fabrication hardware. We already mentioned like many different instances, like regarding the size of your object, which is maybe too big for your printer, the geometry, because maybe it's not aligned or cannot be possibly aligned in a nice way with respect to the build direction. So a nice solution can be to split and then reassemble the pieces, or to overcome the limits that, for example, you have like a cheap printer which handles only one material at a time, and you have a composite object with multiple materials, so you can split it into different parts of homogeneous material, and so on and so forth. When we talk about decomposition, well, I wanted to introduce this slide from 1983. This is a paper which is about the composition of 2D polygons. It has nothing to do with 3D printing. This is just to say that anytime we want to compute an optimal decomposition with respect to some geometric criterion in 2D and even more in 3D, the problem is very likely to be NP-hard, which means that solving it optimally is kind of difficult. We don't want to do that. And so we're going to use some heuristics to drive the decomposition of our objects for fabrication. All the approaches, despite the differences in the various technologies, aim to control more or less these two aspects. They want to control part size because the part has to be ultimately small enough to fit the printer, and also they want to control the local surface orientation. Part size, despite the size of the printer, can be intended also in a broader sense. For example, when you have assemblability problems because you decompose your object and you want to make sure that everything has to be recomposed together, you may want to consider, for example, the extrusion of the parts through a temporal sequence in order to make sure that it is possible, physically possible, to reassemble the object. So it's part in a larger sense, if you want. There are three main approaches to shape the composition for fabrication. One is based on the use of binary space partitions. One is based on the use of graph labelings. And then there are also approaches that use mesh booleans to split the object into simpler pieces. So we're going to say something about each of these approaches. First of all, binary space partitions. Here you just have a mosaic of different papers that use this technology to address size issues, surface fidelity issues, or packing for shipping. And these binary space partitions can be computed either top-down or bottom-up. Both solutions are possible, and we're going to see actually both of them. So let's start with bottom-up. Let's say that this is a very simple mesh that we want to create. What these methods try to do is to generate a tree in which in the leaves you have the atomic elements of your mesh, triangles, tetrahedra. It depends on how your mesh is represented. And then what you do when you move one level up in your hierarchy, you just want to cluster elements based on the adjacency of the mesh. And so you continue until you hit the root in which you have the whole mesh. And so the idea is that at some point you will position yourself at some inner level of this hierarchy, and this will give you like a decomposition of the object. And if you have constructed this tree, taking into consideration geometric problems that relate with fabrication, the decompositions that you have in this tree are suitable for that particular fabrication problem. And so the question that you ask yourself anytime you need to build one little piece of this tree is, what is my merging policy? How do I merge different elements? One representative example of these categories, for example, shapes in a box, which is a paper that Marco did back in 2015, if I remember correctly. And in this case, the tree is constructed in order to minimize a measure that is called absolute aboxiness. So what you want to do in this case is to compute a decomposition in which every single piece is as boxy as possible because you want to do packing. And this measure is very trivially the difference between the volume of the smallest bounding box, which is enclosing your cluster of elements in the mesh, minus the volume of the mesh, of that portion of the mesh itself. So if the portion of your mesh is already a box, this measure is 0. If you have, for example, a very elongated thing, which will be positioned in the diagonal of a box, then this measure is the difference between the volume of that piece and the volume of the box. The alternative is to go top-down. In this case, again, in the root, you have your initial mesh, and now you want to construct your tree starting from the root and going down towards the leaves. So what you do is that anytime you think that your current node is too complex for your fabrication problem, you cut it, and so you split it into parts. And you just iterate this process until you're happy with all the leaves in your decomposition. So in this case, the solution of your decomposition problem is in the leaves of the tree. And once again, everything boils down to choosing a proper cutting policy. A good example for these top-down approaches is Chopper. Essentially, what Chopper does is to take a slicing plane and to split the mesh in two. And the metric that they use to decide what is the best cutting plane to halve an object is kind of a mixture of different ideas. So you want to keep an eye in the number of parts. You want to make sure that the parts are thick enough in order for you for having room to position the connectors, which are like especially the negative part of the connectors, which are going to be like curves in the part. And then they also consider the structural fragility of the object and the aesthetics. So you don't want to have horizontal cuts in very visible parts of the shape, and so on and so forth. So they consider this metric for a bunch of different cutting planes, and they just select one cutting plane which is the best suitable for that particular problem. So speaking about how we explore this space of solutions, there are two main approaches which are actually related to one another. The simplest one is to be greedy. So anytime I take the best splitting plane, for example, or anytime I take the best cluster that I can take. And that can be a solution. The alternative solution, which is called beam search, you can think of beam search as like being a greedy plus. Essentially what you do is not to consider always the best possible solution, but to consider the n best possible solutions, where n is a parameter of this algorithm and is what is called the beam width. So the idea is that essentially you're assuming that your partial solutions can be ranked, and so you rank them and you just propagate solutions considering the n best current solutions. And this is like a pictorial representation of the solution space that you explore. So every single node in this tree is a solution. If we talk, for example, about Chopper, you can imagine that every single arc in this tree represents a candidate cutting plane. So you do the cut, you evaluate your metric for all the possible cutting planes that you have, and you take, in this case, the two best cutting planes, not the best one. If I took just one, that would have been the greedy approach. In this case, I propagate two. So you propagate two solutions. Again, for these two solutions, you consider all the possible cutting planes. Now you get these many solutions. You rank them, you take the two best ones, and you continue with this approach. So at the end of the day, you have explored a larger portion of the solution space, and so you are more likely to have found a local minimum that is better than the one that you found with the grid approach. Although there is no guarantee, there are counterexamples in which, for example, with the grid approach, you can find a solution which is better than the one that you found with beam search, even though you're exploring a larger portion of the space. Another alternative is to compute a decomposition by solving a labeling problem. In this case, you consider your mesh as being a graph, G, with nodes and arcs, and you want to typically minimize an energy which looks like this. You have a so-called data term, which is essentially the cost of assigning a label L to the node I of my graph, and you have a smooth term, which is the cost of assigning the labels I and label J to two adjacent nodes in the graph, Ci and Cj. Okay? So this is known to be an NP-complete problem, but there are good heuristics to resolve it. And it's a type of formulation that has been extensively used in computer graphics and computer vision, for example, for image segmentation, polycube construction, and a lot in fabrication as well. So when we talk about fabrication and labeling, the graph is typically the dual of the mesh. So if you have a surface representation, every node in the graph is going to be a triangle. If you have a volumetric representation, every single node in the graph is going to be, for example, a tetrahedron of your mesh. And the arcs of the graph represent the adjacency. So two, for example, face adjacent tetrahedra will be connected by an arc in the graph, just the dual graph of the mesh. And then the labels typically represent the machining or the extraction directions. And so this is the energy that is minimized. The data term typically looks like this. Every single label represents a candidate machining direction. And in case of infeasibility, like this, for example, this portion of the, yeah, you can see the mouse. This portion of the surface cannot be machined by this direction because it is covered by this part. So in this case, the data term will be infinite, so that you cannot apply that particular label to that piece of the object. Otherwise, you have a function that will give you like the easy of machining that particular portion of the mesh from that particular angle. And so you want just to minimize this. On the other hand, you have the smoothing term, which is typically 0 if you are assigning the same label to two adjacent elements in your mesh, and it's going to be some other function otherwise. So this is kind of a regularization term in which you want to weight essentially how many blocks you have in your decomposition and how many, essentially the extent of the boundaries of the decomposition. The more this dominates this, the less boundaries you will have in your decomposition. This is kind of the flavor of the balance between the two terms. And as I said, this has been used a lot in fabrication to compute decompositions. For example, for computing the composition of multi-material objects into pieces of single material, height field decomposition for CNC milling with 3 axes, with 4 axes, molding. All these decomposition algorithms internally resolve one or more instances of this labeling problem, essentially. Finally, for Booleans, I'm just going to give you an example about a single paper that uses them. This is like less used with respect to graph-based approaches and binary space partitions. Here, the idea is that essentially you kind of decide with Boolean operations what portions of the shape you want to detach. In this case, the goal is to decompose this object into height fields, so something which has a flat base and can be machined from the top to the bottom, reaching every single point on the surface. And so what this method is doing essentially is to compute maximally grown boxes, which detach a portion of the object which is a height field. And of course, there are way too many boxes here. So what they do is to compute a minimal set cover to make sure that every single portion of the shape is covered. And then they perform Boolean operations to compute the final pieces. So now every single piece here is a height field and can be fabricated with a C-axis machine with 3 degrees of freedom. Okay, so now just a few words. Let me see. Yeah, just a few words regarding the generation of the toolpaths. So as I said in the beginning, I did a distinction for the 3D printing machines between vector machines and raster machines. When you have raster machines, the slices are essentially binary images. So there is no notion of toolpath because the slice is created like all together. When you have a vector machine, you have to decide whether it's going to be like the extruder that is depositing material or the laser that is passing through the surface of the tank containing the powder of the metal. You need to decide what these paths are. And so there are a bunch of different ways to fill a slice with some paths that internally cover the interior of the slice. And this is like a good representation of these machine tool paths. You can have like zigzag, which go from one side to the other. You can have like nested contours that propagate like a distance field that emanates from the boundary. You can have space filling curves, and you can have spirals, which are pretty much like contours, but they are connected such that you start in a point and you end in a point. You don't have nested curves. What you want to achieve here is, first of all, path continuity. You want to avoid as much as possible to start and stop for example, your extruder, because anytime you start and stop, the deposition is not homogeneous. So you want to link the paths as much as possible to avoid to stop your extruder or your laser. And at the same time, you want the geometry of your paths to be nice and smooth, because this promotes an homogeneous deposition of the material. So you create better slabs of material when you fabricate. Just a tiny observation, all these paths here can be easily derived from a distance field. So this is indeed how they are defined. In terms of optimization, when you solve machining toolpath problems, you want to be, so one thing to keep into consideration is the time that you need to complete, to fill the slice with your tool. And so in this regard, of course, you cannot avoid the time that is necessary to deposit or solidify the material in the slice, but you can minimize what is called the air time, which is the time that goes from the end of a curve to the beginning of the other, because that is the time in which the machine is not operating, it's just wasted time. So it turns out that optimizing for this time relates to the traveling salesman problem, which is an NP-complete problem, so it's a very complicated problem in optimization. And you can solve this through heuristics. One particular type of machine tool path that has been very popular in the graphics community since 2016 when it was introduced is the Fermat spiral. These tool paths have been very popular for two reasons mainly. First of all, allow you to precisely control where to begin and where to end your spiral. And this is very easy this allows to optimize, as we will see in a second, various aspects. And the second thing is that it naturally promotes very low curvature paths, which is nice and ideal for homogeneous deposition. The way these paths are created, as I said before, is through the generation of a distance field. So let's say that this is the slice that I want to fill. I generate a field that propagates from the boundary towards the interior. And the topology of the contours essentially decomposes these ISO levels into different pieces, which are calling here islands. Then these islands are connected to one another in order to create a final spiral. And you can see pretty much here where the link happened. And so essentially this is a single spiral that is covering the whole slice and is aligning to the level sets of the distance field. But the main difference, I don't know if it is visible here, but here you have like lots of nested paths, and here you have one single path. So that's the beauty of it. As I said, this is computed through a distance field. So this is a distance field of a real slice for the armadillo model. These are the level sets of the distance field, and this is like the Fermat spiral with the rendering of the actual tool paths that have been deposited. Since we can control the begin and the end of the points in which the spiral is defined, we can play with this also to make sure that the deposition is continuous not only within every single slice, but also across multiple slices. In particular here, what I'm doing is to position the beginning and the end of the spiral always in the bottom right corner for every single slice, which means that my head, for example, my extruder, is always starting from there and going there, and so I'm saving time when I compute and when I print multiple slices. Okay, so I'll give you the stage to Marco to conclude.
Yeah, okay, I'll be very quick. And I will try to let you know what's the ongoing research in this area. I hope that what we have talked about has inspired some new ideas for your future research. And here are some suggestions of what is interesting now. As Marco mentioned earlier, there are some labs around the world that are trying to create these devices that use 5-axis 3D printing. Of course, this is, well, as you see, 3 degrees of freedom make it very easy to program your machines, but you have many limitations, overhangs, you need supports that you cannot always remove, and so on and so forth. So these technologies would alleviate these problems. So it's a really interesting area of research. Of course, they are quite expensive now because all these machines are prototypical. So, but yeah, this is where you can work. Another interesting aspect is the simulation of the printing process itself. This is where you can predict where your material being deposed would deform, and you can predict the residual stresses that would remain within the object, because then you might want to use that object and you don't want it to break during usage. Or you can predict the breaks during the printing process itself. So everything, all this area is very interesting. It's mostly an engineering-related part, but there are aspects that are geometric that can be studied. Multi-material printing. Here, the biggest problem is to make it easy to model these objects. The fact is that currently, there are printers that mix up various materials and made it possible to create graded colors or graded levels of flexibility, of elasticity, of transparency, and so on and so forth. So printers are able to, or already today are able to do that. The difficult problem is to create modeling tools that enable you to create these molds. And actually, some tools allow you to create multi-body objects. So you create one part that is supposed to be made of one material, one other part which is supposed to be made of another material, and you compose these parts. But if you want to create graded materials or global microstructures that gradually behave in a different way, that is much more difficult. And here, probably, there's room for further improvement from our community. Another interesting aspect here is multi-material meshing. Well, meshing is difficult. Even if you consider one single material, meshing is a difficult beast. And if you plan to create volumetric meshing that consider interfaces between materials or even graded material properties, this is something that can be really interesting, because now, and this can support the simulation of the process for multi-material printers too. Okay, so I conclude because it's quite late. What we have seen is that, unfortunately, today, creating 3D models is not as easy as drawing. So this is something that must be considered for the future. And when creating these modeling tools, the fabrication technologies must be taken into account. And knowing in advance that the model must be built using a specific fabrication technology might be a help in designing the model itself. Physics must be considered for example, for simulating the process or for simulating how the object will behave after printing, or to choose the best tool path or whatever. The whole process planning, pipelining is something that still needs research, because each of the steps we have discussed is not completely a closed problem. So there is something interesting to study there. This is, well, the message I hope to have delivered. There is room for many other contributions in this exciting area. And okay, this is all. Thank you for your attention.
Yeah, and of course, have time for a question.
Yeah, thanks a lot. Do you have an idea about the size of market for vector versus raster? So what is done in practice? Is it 50-50 or is one much more important than the other?
This is a very good question. My feeling is that vector is dominating. I don't know what you think. No, I don't know. I don't really have clues. My personal experience is that vector is dominating, but of course I cannot say that. I did not make a statistic.
I mean, maybe there are more challenging and interesting problems, but maybe it's not what's done in industry. So that's a little my question.
Well, of course there are challenging problems, but I don't think it's a matter of challenging problems. Actually, it's a matter of how technology is designed up to today. Well, this is how things work. So, yeah. Well, I'm sorry, but I don't have many clues about that.
I was just curious, you had the slide where you said what you were not talking about, and you mentioned sort of like stresses in the object. I was wondering if you could elaborate on that. Like I wasn't sure what you guys meant generally, yeah.
Well, it's quite early.
I think you meant the residual stresses for metal plating?
Sure, if that's, yeah.
So what happens is that when you print the metal, you reach very high temperatures. And so one of the major issues is to how to essentially make sure that the product doesn't break after the print. Essentially what happens is that when the object cools down, you have lots of internal forces which are given by the effect that the object is cooling down. And this may lead to breaks in the metal. That's why, for example, I didn't say anything about this, but for example, for the orientation part, orientation for metal printing, it's a topic by itself. So the way people working in metal fabrication orients objects is completely different. For example, when I showed the ideal shape, I was saying, okay, if you put it like perfectly aligned, it's the best thing. It's true for most of the technologies. It's absolutely not true for metal. For metal, they would put it in diagonal. Like if you were a guy printing on metal, you go for that solution. And I cannot really give an exhaustive explanation for this, but talking with people who like operates metal machines, what they told me is that essentially they look the slices one on top of the other, and they try to make sure that the subsequent slice is like sitting as much as possible on top of the previous one, because in terms of effect of the cooling down, this is like the best thing that they found heuristically. I was super interested at some point to make some paper about like optimizing this thing, but it was really difficult to, kind of formalize what they were trying to do, because they do it manually. And the guy was like, okay, you scroll a bunch of slices and it's like, no, this is no good. And then you try to understand why, but it's like, it's really puzzling in a sense. It's like dark magic.
Yeah,
But
they do that on the ground, and
Yeah.
for them it's like an art, it's not science.
And the
Try to
major
understand.
issue is that is like handling the temperatures, because when it cools down, it breaks.
Okay. Yeah, I feel like we have a lot of works in the community that like try to, model, heat diffusion and stuff. I was wondering if like, yeah,
Yeah,
maybe there could be useful ideas from the community. I don't know. Yeah.
The problem there is that it's a very difficult problem because it is dynamic. It's not a heat diffusion in a static model. It's something
okay.
that moves and the heat evolves and material is added all together, so it's very complicated.
Sure. All right. Pardon my ignorance on this, but on the slide where you showed different approaches to external supports, one of those was Photoshop. Was that?
Photoshop CC.
I'm sorry?
Photoshop CC.
Yeah, that's a 3D modeling. That the Adobe software, the image editing, that does 3D modeling. Wow, that comes as a surprise.
Can you go to the slide where you showed the spiral two paths? Especially like the place where you have like the same starting points. I was just wondering, typically how much time do you save by like trying to optimize on the starting points?
So, this one?
No, yeah, that one.
That one?
Yeah.
Okay.
Do you have like a sense typically how much time you save by optimizing on the starting point? I'm guessing that's like a optimization for time.
So this comes from a paper, it's a recent one, which is called As Continuous as Possible. I don't remember how it ends, like Fabrication or something. So I remember they have like pretty good results in terms of total optimization of the process. If you ask me this specific thing, how much impacts, actually, I'm unprepared right now. I don't know how to answer that. I can take a look at the paper again and let you know, because, you know, as far as I remember, they were able to save something like 30% time, but it's like a global value. It doesn't necessarily depend only on this specific thing. This is one of the tricks that they use, and to some extent impacts, but I don't know the precise extent right now.
For the linking, you just said moving over the diagonal in one slide.
For the linking, yeah.
For the blue column, so when like this, I go down to the next level and I start immediately where
Yeah, that's the point.
Hi. Well, I have a question about the decomposition. Is there a model that leverages which parts can actually fail during a print? So it splits the model based on what you might need to reprint if you have to change the parameters for certain parts?
I'm not sure I understood the question. So you are asking if exists a decomposition model which optimizes for failure?
Yes, exactly. Like which parts of the model are more likely to fail based on the angle, the structure, detail that they have, and if it separates those in case of failure to change parameters for later reprinting?
Okay, not that I'm aware of. I don't know any specific algorithm that optimizes for that. But in reality, these algorithms, if you think about them, they're like meta algorithms. You can optimize any functional. So whatever is your desiderata, you can just use that particular scheme. So in the literature, as far as I know, there is nothing like this, but you can apply like the same approach to optimize a different functional that could be done.
Okay, thank you.
Maybe we can save the remaining questions for offline.
Okay.
And we can start with the first talk. The next talk is at 11.
Thank you.